Hello everyone, welcome to our first virtual classroom, Chapter 10, Section 1. The class where you can sit in your recliner, eat snacks, text your friends, talk to your mom, spit spitballs at the screen, and I will never know. I don't recommend that you do those things, certainly not at once though tonight. So this is going to be our first attempt at the flipped classroom. I'm going to teach the lesson, and then we're going to come to class and apply the lesson. The lesson is in Chapter 10. We are studying circles. Now, we should understand why we might study circles in mathematics. Circles are very easy figures to understand. There's only a few different measurements about the circle. The triangle, we've studied the triangles. They are simple figures as well. That's why we study them. There's only a few movable parts. Notice as the figure gets more complex, let's say even the quadrilateral, which we have studied some, but notice we haven't talked a lot about formulas for the quadrilaterals. We've talked about different properties. We haven't even touched the pentagon for the most part, because look at all of the different varying quantities here. It's a very difficult shape, and the more sides you get, the more complex it gets. But circles are not. We've got circumference, we've got radius, we've got diameter, we've got center. So that's going to lend itself to a lot of relationships that we can study here. So let's go ahead and get started. There are three theorems that I want you to record in your theorem notes, in your pink booklets. So get those pink booklets out. Go ahead and follow along. Act like this is class there at home. Take notes, but you won't have to take copious notes, because if you need to stop and replay what I said, if you dozed off, feel free to replay and try it again. If something doesn't make sense, give it another try. So we're going to investigate Theorem 74, and I've written in blue, like I normally do, the given. If a radius is perpendicular to a chord. So let's record, let's first look at our given statement. We deal with a radius perpendicular to a chord. We must have a circle here. We've got to have a circle, we've got to have a chord, we've got to have a radius. So I'm going to go ahead and create that circle. There's our circle. I'm going to go ahead and put a radius on there. I'm sorry, a chord, and now a radius. Here's a radius there. So I've got a radius, chord, and circle. I think I didn't quite get that. Try this again. There we go. There's my radius. I can swing this radius around. In fact, where should I put this radius? According to this theorem, I'm looking at the specific situation if a radius is perpendicular, right there, perpendicular to a chord. What do you suppose I should finish the red sentence off with? If it's perpendicular, what must be the case? Well, we can investigate this a little bit here. We're going to investigate this. I'm going to make sure this is perpendicular. So there's my angle, not quite perpendicular. Let me adjust that. 89, 90. There's pretty close. Call that perpendicular. So I'll do this in blue. That is perpendicular. And what now do we conclude? What do you think? Some of you, I can hear you saying, Mr. Kaufman, you need to measure the chord and see if we've bisected it. Yes, you're right. Let's do that. So now I'm going to measure that distance here. The distance from G to E is 3.5, and the distance from E to F is 3.45. Ooh, we're pretty close. Well, I can see here I'm not quite perpendicular, so let's try to adjust that to get more accurate. 99. Pretty close, aren't we? 3.49, 3.46. Here's the theorem. Look at the blue and the red. If given the blue, what's blue? Radius, a chord. perpendicular relationship, then what is the conclusion? Red is the chord is bisected. Okay, so let's go ahead and write that in our booklets. If a radius is perpendicular to a chord, then it bisects the chord. That's what we learned. Okay. Now, I have. Let's see if this works again. If I were to move this chord around, let's erase these markings and move this chord around. Let's try this chord right here. All right. Now, what am I going to be looking at? I'm going to be looking at. I will make this color blue because that's my given. This is my given. These two are my conclusions, right? So I'll be looking for those in red. So let's first worry about, sorry about that. Let's worry about this guy first and try to get that to be 90 degrees. I'm looking at my blue degree. It is right there at about 90 degrees. Now let's look at my red. Yes, it appears that 4.66, 4.67, I have bisected it. So again, my blue is if perpendicular, then bisecting. Okay. Now we have done an inductive investigation of this theorem. We have not deduced it, but we have induced it. Let's move on to the next theorem, Theorem 75. You're going to find it to be very similar. Theorem 75. Again, if a radius of a circle, so we have to have a circle with a radius, and now we're going to bisect the chord, and that chord is not a diameter, so that's what we call a disclaimer. We'll look at that afterwards. So let's go ahead and construct this. You probably are already racing to the answer, and that's great if you know what the red phrase needs to be to conclude it. But let's go ahead and do this. If a radius, so I need to have a radius, that's given, of a circle, that's given, bisects a chord. I'm sorry, I've drawn my chord. Here's my radius. There's my radius. Remember, radiuses can be any I can place it anywhere. Now, how does this need to be placed? It must bisect that chord. So I'm going to help myself out here, and I'm going to construct the midpoint so I can see that bisection. Now let's go ahead and place it so it's bisected. All right. What do you think is a resultant? So here I am given bisect, and what do I conclude? You guessed it, perpendicular. It is simply the bicondition of the last theorem. So let's write that in words then. So if a radius of a circle bisects a chord that is not a diameter, then it is perpendicular to the chord. Now, why is that disclaimer important? Well, let's investigate a chord that is a diameter. Okay? So I'm going to investigate a chord that is a diameter. So if I take this chord and make it a diameter, we'll look at that. Does the radius and the chord necessarily have a perpendicular relationship? No, not at all. But as soon as that chord is not a diameter, then it does. See, I will move this here again. I need to put my radius right through that point, and it will be perpendicular. Perpendicular. Okay. So we have the first two theorems basically say this. The first one went from perpendicular, and it implied bisection. And the second one started with bisection, and it went to perpendicular. Here are the two theorems that you need to commit to memory and be able to apply. Both of these theorems have to do with radii and chord relationships. Let's move now to theorem 75. This will be the last theorem. I'm sorry, 76. Okay, I'm given a perpendicular bisector of a chord. So let's again read this carefully. I'm given perpendicular bisector of a chord. So again, I must be in a circle world here. So let's grab a circle. There's my circle. I'm given perpendicular bisector of the chord. So I need to create a chord. Here's my chord. I need to find the midpoint of that, so it's perpendicular bisector, and now I'm going to create the perpendicular bisector of that. And before I do, what's gonna happen with this perpendicular bisector? Can you finish the red statement, the conclusion? What is going to be true about that perpendicular bisector? Yeah, I heard it. You said it under your breath. You said it's going to go through the center, and it sure did. So take a look at that. Here's my given. I'll mark it in blue. My given is perpendicular. I'm sorry, my given is yes, perpendicular and bisecting. And what do I conclude? I'll circle it. Pass through the center. Let's animate the circle a little bit and look and see that that's going to always be the case. Whenever I have a chord, it's a perpendicular bisector, it will pass through the circle. And it doesn't matter if it's the diameter. I mean, that's kind of actually the obvious situation. It will always work like that. Okay? So let's write our response there in red here. Then it passes through the center of the circle. Passes through the center of the circle. 3 theorems to commit to memory. Now let's look at some examples. Okay, let's go right to examples. Again, you're welcome to rewind, rewatch any of that that's necessary. Look at example problem number 1. Circle C below has a radius of 5 centimeters. So we have a radius here. Now I don't have a radius marked, okay? So let's go ahead and pencil that radius in. So here's my radius. Remember, radii can be drawn anywhere on the circle, but that radius distance is 5. In fact, we can go ahead and measure that. Distance is, there it is, FC is 5. Okay, now is 5 centimeters in length when chord DE is 8 centimeters long. Oh, so this chord here is 8 centimeters in length. What is the distance from point C to DE? Alright, now when we talk about distance from a point to a segment, what we are always referring to, and I'll mark this in red because this is what I'm trying to find, I'm always looking for the perpendicular distance. The perpendicular distance from C to that segment DE. Now some of you have raced to the answer already. I want to know the distance of the red one. Well, I'm going to be clever about where I position my radius, and I see now that that is a what type of triangle? A right triangle. And that triangle has, what are the side lengths? Well, we know that this has got side length 5. This leg here is going to be 4. Why is it 4? Well, we have a radius. This could be a radius that is perpendicular to the chord, therefore it bisects. So this is a what type of triangle? a 3, 4, 5 triangle. Answer, 3 units. So what we have done is we have taken the theorems of the section and we have applied it in a mathematical situation. And we can see here where we have seen we've made some right triangles. So you can expect that right triangle concept to be applied in this chapter because of these nice theorems, relationships between a radius and a chord. Let's move on. Let's go on now to the last example problem, and this is going to be a proof. Example proof. So here's the situation. I've got circle A. We can see over here circle A is, and we've got BC is perpendicular to DE, so I've put the blue there, the markings there. What do I want to prove? I want to prove that DB is congruent to BC. That's not supposed to be BC. Pardon me while I make that DC. I want to show that those two side lengths are the same. Now never forget that this really is a dynamic situation. Okay? This is really in motion. Just what is preserved is the relationship that we've marked there, that DE is perpendicular to BC, and we want to prove that those are congruent. Well, let's do that. Where do we start? Well, just using our theorems, we notice that whenever we have radius perpendicular to a chord, we know it's perpendicular, therefore we know bisection. So our first conclusion is that BE is congruent to EC. Why do we know that? Well, if a radius is perpendicular to a chord, then bisects the chord. Now what? I'm going to erase that. We're trying to find that. Now what do I know? Well, we've got the trusty reflexive, right? DE. DE is congruent to DE. That's our reflexive. We also have that angle DAC. This angle is congruent to this angle because right angles are congruent. So angle DEC is congruent to angle DEB because right angles are congruent. And now we can say triangles are congruent, can't we? Triangle DBE is congruent to triangle DEC by side, angle, side. And that now allows us to say that BD is congruent to CD. And we have deduced now that those must be congruent CPCTC, and we have proven what we wish to prove. This concludes the lesson. Hope that was favorable. You have 3 theorems to review and to know and to apply, be able to work these types of problems, and then tomorrow we'll take it a step further in class. Good night, everyone.